According to the standard cosmological model, the universe began expanding with the Big Bang. In the earliest moments, this expansion was faster than the speed of light. Then, the universe continued to expand at a slower but steady rate. This led to the widely accepted idea that the universe would expand forever. The driving force behind this expansion is something we still don't fully understand. Dark energy, a mysterious influence that acts constantly and unchangingly across space. But what if dark energy began to decline one day? If that happened, the expansion rate of the universe would slow down. Eventually, gravity could overpower it, reversing the expansion entirely. However, until recently, we had no solid evidence suggesting that dark energy changes over time. Then something changed. In 2018, the first results from the Dark Energy Survey were released. These findings appeared consistent with a constant dark energy model, but also showed that variable models couldn't be ruled out. In 2021, data from the Planck Institute, DESI, and the Hubble tension were combined. The results revealed discrepancies in the expansion rate, also known as the Hubble constant, which led to speculation that dark energy might not be constant after all. By 2023, researchers analyzed data from Type I supernovae, galaxy clustering, and baryon acoustic oscillations. They found that the evidence favored a time-varying dark energy model over a static one. Then came February 2024. Data from approximately 15 million galaxies suggested that dark energy may have decreased by about 10% over time. While these findings caused confusion in the scientific community, most researchers were hesitant to abandon the standard model. But a group of physicists from Cornell University, Shanghai Jiao Tong University, and other institutions began preparing to say what many were thinking. The elephant in the room could no longer be ignored. In July 2025, these scientists published a study applying the decreasing dark energy data to the classical cosmology model. According to the paper, the universe would not expand forever. Instead, it would eventually contract, collapsing back into a singularity in approximately 33.3 billion years. So, perhaps the idea that the universe expands eternally was never quite right. After all, the concept of infinity is hard to grasp with human intuition. For us, everything has a beginning, a process, and an end. Maybe that's why the idea that the universe could one day end feels more natural. At this point, it was precisely these intuitive limitations that led Nobel laureate Roger Penrose to the idea of a cyclic universe model. Put simply, the idea goes like this. The universe begins to expand, this expansion gradually slows down, and eventually, the universe starts contracting. Each cycle has its own beginning and end, but no information or entropy passes from one cycle to the next. Every universe starts completely fresh. However, due to the lack of strong evidence for a dynamic dark energy, few physicists embraced this idea at the time. Now, that gap may finally be closing. A recent study with the potential to shift the cosmological paradigm has just been published. The current cosmological model, including the Big Bang, is known as the lambda CDM model. It assumes that dark energy is responsible for the universe's accelerated expansion. According to this model, roughly 70% of the universe consists of dark energy. But what exactly is dark energy? It's a reverse-engineered concept. We can't observe it directly, but infer its existence from its effects. We know the universe is expanding, and we can measure the rate of this expansion. From that, we conclude there must be some invisible force driving everything apart, and we call that force dark energy. Imagine this. You've placed some dough in the oven. You don't know the oven's temperature, but you can clearly see the dough rising. You naturally conclude that it's not expanding on its own. There must be heat causing it. That's how we infer dark energy, by observing how the universe behaves. In the lambda CDM model, dark energy is constant. To make it concrete, imagine that its strength is always a fixed 10 units. It keeps pushing the universe outward with the same force. That's why expansion continues indefinitely. But if you lower the oven's heat, the dough would rise more slowly. Likewise, scientists have begun asking, what if dark energy isn't constant? What if, as recent data suggests, it's actually decreasing? A cosmological model attempts to explain how the universe began, how it evolves, and what its future holds. The most widely accepted model is lambda CDM. Here, lambda represents the expansion rate, or the strength of dark energy. The other components are matter and dark matter, which represent gravitational attraction. To build a reliable cosmological model, we need to understand the balance between these three components. At this stage, scientists have stepped outside conventional thinking and proposed a negative cosmological constant. According to the authors of the study featured in this video, the new data suggests that dark energy is not constant. It may vary over time, and at some point, could even turn negative. This assumption opens the door to a scenario where the universe's expansion halts and ultimately reverses into a collapse. In doing so, this paper not only highlights the dynamic nature of dark energy, backed by data, but also presents a bold and thought-provoking challenge to the prevailing assumptions about the universe's future. At this point, it's worth explaining the concept of the axion, which plays a crucial role in this model. If the model had included only a negative cosmological constant, the universe would have never expanded, it would have collapsed immediately. To address this, the researchers introduced an axion field associated with an ultralight particle found in quantum field theory. This axion field carries a large amount of energy in the early universe. That energy temporarily suppresses the contracting force of the negative cosmological constant. As a result, the universe begins a period of rapid expansion, similar to what we see in the standard cosmological model. According to the paper, the magnitude of the proposed negative cosmological constant is about 100 times smaller than the positive value in the lambda CDM model, but with the opposite sign. In other words, weaker in magnitude, but opposite in effect. The universe is currently around 13.8 billion years old and still expanding. But under this new model, that expansion won't continue forever. Roughly 7 billion years from now, when the universe reaches 20.8 billion years of age, expansion will cease. That will mark the universe's maximum size. Afterward, due to the effects of the negative cosmological constant, aided by the axion field, the expansion will reverse. The universe will begin to contract. This contraction phase is expected to last approximately 13 billion years. Eventually, when a universe is 33.3 billion years old, all matter, energy, and space-time will collapse into a single point. This dramatic finale is known as the Big Crunch. The paper argues that this scenario is only possible if dark energy is not constant, but instead has a time-varying nature. Now, this raises an important question. Is this just a theoretical suggestion, or is the model consistent with current observational data? This was something I was personally curious about, so I carefully examined the study from this perspective. Here's what I found. The authors clearly state that their model does not contradict existing observational data. In fact, they claim that the combination of the axion field and negative cosmological constant can produce a cosmic expansion history that aligns with certain large-scale astronomical observations. However, and this is crucial, the language used in the paper is quite cautious. They don't declare that their model definitely fits the data. Instead, they emphasize that it does not conflict with the data and may potentially match observations. In short, the model remains speculative, but is grounded enough to be taken seriously. Although the paper presents a bold and provocative approach, it's important to recognize that the proposed model relies on something not yet experimentally verified, the axion field. This makes the model incomplete and open to debate in certain respects. However, we must also remember this. Dark energy itself has never been directly observed either. It's not a confirmed entity, but a derived concept, inferred from the universe's accelerated expansion. The essence of the matter is this. Scientists have now reached a point where they can seriously compare unconventional theories, like cyclic universe models, against both mathematical frameworks and observational data. In that sense, saying this new perspective offers no promise would be unfair. Quite the opposite. It's a timely and intriguing development. And here we are, science enthusiasts, bringing you insights from a paper published just 1 week ago. If you enjoy our content, please like, share, hype it up, and consider clicking the join button. That way, we can reach even more curious minds out there.